This is a carefully made model of a Bermuda racing yacht being pulled along in a ship model towing tank. As it moves through the water, instruments measure the drag of the water along the hull. These measurements, fed into a computer and combined with wind and sail information, can now be used to predict the yacht's performance in an actual race. How modern naval architects are using facilities such as tow tanks and computers to get an ever faster sailing yacht is our story today on Science Reporter. Hello, I'm John FItch, MIT Science Reporter. Today, we're at MIT's ship model towing tank in Cambridge, Massachusetts, to learn what new techniques naval architects are using to design ever faster and faster sailing boats. The famed 12-meter boat is without doubt the aristocrat of the racing fleet. Her sleek hull usually runs about 70 feet with a mast nearly twice that high. She's generally crewed by 11 men and alone is eligible to compete in that most revered of all yachting contests, the America's Cup race. Back in 1851, the visiting United States schooner America led a fleet of British boats around the 53-mile course off England's Isle of Wight, coming home with the Royal Yacht Squadron's Cup. 4 years later, the victors gave the cup as a perpetual challenge trophy and provided probably the greatest single stimulus to the continued development of yachting. Before 1870, yachts were usually turned out by rule of thumb, each builder having his favorite type. Once the cup races were on, the infant science of naval architecture came to be applied to yachting. Names like Smith, Burgess, and Herreshoff were linked with one successful design after another. Certainly no less important than the revolution in hull design was the development of modern rigging. By 1920, aerodynamic principles were being applied to sail plans, and tall, narrow sails with long leading edges replaced the old broad-based gaff rig. Large parachute-like spinnakers supplanted their small, flat predecessors. One might suppose that after giving the racing yacht more than a century of well-focused attention, naval architects would consider this a job well done. This is far from the case in a world where tenths of knots can make winners of losers and vice versa. To learn more about how naval architects are making use of modern design techniques to catch up with these elusive fractions of knots, we talked with Mr. Halsey Herreshoff, an instructor in the Department of Naval Architecture at MIT.
Well, in the design of any racing yacht, there are two factors that are most important. Number one is the sails, and secondly, the hulls. The sails have to be designed or trimmed in such a way that there's a large forward thrust, hopefully without a large side force. And the hulls, it's most important that they be designed and shaped such that the drag force, or the resisting force of the water to its motion forward, is small in order that the boat can sail at high speed. For a hull such as the one we have here, which is a 1/10 scale model of a 40-foot racing boat, I think you can see that for the designer there are many possible choices. He can have variation of beam, or of draft, or of the shape of the sections, or the way the sections are combined. And so I think from that it's evident that it's quite a difficult problem to decide what is the best boat, or secondly, once a boat has been designed, it's quite a problem to determine how it will perform, what the drag side force would be on the hull.
This isn't something that you could write a nice little mathematical equation for and put it in a computer and come out with the best design.
No, I'd like to say that we had a way of doing that, but unfortunately, since we can't do that, at least yet, we must resort to experiment. And that's why we make these scale models of proposed designs and tow them in the model tank, measure the forces, and from that means make a prediction of the full-size forces and performance.
Well, let's talk about some of these forces that you might measure. What would they be?
The forces on the hull are really such that we can divide them into two portions. There's, first of all, a frictional drag, which is the resistance caused by friction of the water moving along the surface of the hull. And in addition to that, there is a wave drag.
It's a wave drag.
Well, that is the force that is required for the energy that is used to form the waves that are familiar going along behind any ship or hull that's underway.
Well, that's just wasted energy then. I never thought about that.
Well, that's right. Those waves which
Look so pretty.
well, they look pretty to people, but it's the object of every naval architect to reduce those waves, because by reducing the waves, he can also reduce the drag and have a boat that will perform better.
Are there any other things that you'd want to measure?
Well, yes, there are. Not only is it important that the hull have a small amount of drag, but it should be such that it has a considerable resistance to motion to the side. And that is why we build the hulls with a keel of this form, and in some cases even an extra piece below, in this case a centerboard, which resists motion to the side. This can go up and down, and when the boat is sailing in such a way that you want to resist side force, it's put into the position shown here.
And what is this? What causes this side force that you have to resist?
Well, the side force is a result of the forces on the sails. Unfortunately, even the best sails, in order to have a satisfactory force forward, have along with that a considerable force to the side.
That's right. You're not always going right along with the wind, are you?
No, that's right.
It's pushing you to the side somewhere. I see. Well, why don't you just make this as big as you can until it hits the bottom?
Well, as in all engineering problems, there's a matter of compromise. Certainly, as you suggest, if this came on up a good deal further, there would be more side force possible. But along with that, the drag would be increased. And so the designer tries to choose an optimum combination. And that combination is chosen not only from the standpoint of performance of the boat, but also he must devise a boat that performs well within the handicap system that's set by the rating rules under which the boats race.
For a particular class of boat.
For a particular class of boat, that's right.
Well, now, would an architect just bring you one boat?
No, in order for an architect to really find out very much here, he should bring us several models. And he might bring us this model, or one with a deeper draft, or one with a different shape to the hull. And I can show you another model that we have set up here in the position ready for test. You'll see that as it's located here, it is free in pitch and in roll, much as a boat would be free actually sailing out on the water. And we make a connection of the model to the carriage at 3 locations. This link forward goes to a transducer, which we use to measure the drag force.
Right.
And there are similar transducers, one at the bow and one at the stern, which are used to measure the side force. In each of those transducers is a mechanical, electrical device with lead wires that go up to the carriage and from there to our control station.
Right.
And you'll see that the model is connected with these pairs of arms such that it can assume a variety of attitudes, and those attitudes can be equivalent to the actual sailing conditions.
Could we actually see one of these runs?
Yes, we certainly could. Hank, would you please run the model back and make a run? In an actual series of tests to evaluate a hull, we make runs at quite a variety of conditions. In fact, we make 90 different runs for each hull.
90?
90.
Why would...
Well, that's because we have to try to simulate all the possible attitudes and speeds that we would have for any boat actually sailing. So we run it at 10 different speeds and 9 different combinations of heel and yaw angle. The yaw angle is the angle between the boat's centerline and its direction of travel. This particular run simulates a sailing to windward condition.
What's that? I'm a landlubber, I'm afraid. Is that into the wind? Or?
Yeah, sailing to windward is into the wind, or at least within about 40 degrees of the wind direction. And you'll see the boat is heeled and going along much as she would actually underway.
Well, this is fine in a nice, calm towing tank, but actually a boat would be out in the ocean and there'd be waves and other factors, wouldn't there?
That's right. And while much of our research is done here in calm water, as was the last run, we're now devising ways of making tests in waves. And if you'd like, we could start the wave maker up and show that. Hank, would you start the wave maker, and we'll have waves along with this run. We'll be running the model at the same speed and attitude as last time, but this time we will have waves much...
I can see the waves coming along.
You can see them
my end, anyway.
Starting along here, and Hank will wait just a short time here until the waves get down to the location of the model, and then he'll start it forward again.
All right. This time
You'll notice that the motion of the model in these waves looks rather nervous, rather quick.
Yes.
And that is because the time scale really needs to be adjusted along with the scale of the model in order to have it look the way it would out on the water.
I see. Not only does the boat itself have to be stretched out to become a real boat, but time itself has to be stretched out.
That's right.
Well, how do you do all this scaling up to the real thing? Is it just a matter of multiplying the length of this times the scale?
Well, first of all, why don't I show you the controls that we have in our control room, which we use to measure the forces, and then from there we can talk about perhaps how to expand the results to full size. Let's have a look at the control room.
Right.
Incidentally, many different types of experiments are conducted here, but they're all run in this same control room. These instruments are used to measure the forces. This top one is an electronic counter, and on this we can make a measurement of the drag force. The next one gives the side force at the bow, and this one the side force at the stern. The instruments down below are amplifiers and converters for the signal that comes in from the carriage and then goes on up to the electronic counters. This is a telescope through which we can sight the model and line up some crosshairs in order to determine the heel angle, because of course the heel angle is an important factor. The actual run is controlled here. We have levers that control the speed, and once the run is begun in this fashion, everything goes automatically. There is a switch which is tripped by the model, and as that happens, you see the signal starting to come in. Now the signal for all the forces is summed over the entire period of the run, and finally as the model gets down toward the end, it'll trip a switch which is the end of the run, and that then gives us a total figure for all the different forces on that particular run.
Is that something, is it measured in pounds?
No, it comes out in a number, in this case 22904, which isn't pounds, but it's proportional to the drag force.
Right.
And in order to convert it, we have to divide by the length of time of the run and also by calibrations of the dynamometers. We do that by means of the computer, and the next step after we leave here is to punch the data onto cards, and by that means compute them send them to the computer. This is a sample of the results that come back to us from the computer, and you'll see that the calculations here are divided into columns for the model and others for the yacht.
This is what the computer has predicted over here.
That's right. This is what the computer has predicted based on our model measurements. Here's the run number, and next the yaw and heel, which describe the attitude of the model underway, and the speed, in this case 2.689 knots, and a tow force of 0.812 pounds.
It's not very much force, is it?
Well, it's not very much, but of course it's quite a small model.
Right.
In this case, there was no side force because the model was just running upright and straight ahead. Then, from these values, a prediction is made of the yacht speed, 6.59 knots, equivalent to the slower speed of the model, and we get a drag force, a tow force indicated of 147 pounds.
See, right, and no side force again.
No, we get no side force, but in later runs we will have side force when the model runs at different attitudes.
Well, how do these computed values compare with what would actually happen if you built?
Well, of course, as in any field of research, we're always interested to find out whether or not our predicted values correspond with actual fact. And toward that end, we've just conducted a very interesting experiment. We made a full-size test of a 32-foot boat, and the picture here shows that boat positioned at the David Taylor Model Basin down in Washington, D.C.
This is not a model, this is a full-size boat?
This is an actual boat,
Must
32
be a
feet long.
tremendous towing tank.
Well, it is. The tank is about a half a mile long and 52 feet wide. You can see a person standing here that puts it into scale.
Right.
And the boat is mounted there just as we would mount it here in the tank, and we've conducted full-size force measurements and are making comparisons between those and equivalent measurements made here at the model tank.
And how does it look?
We haven't got the results completely finished yet, but preliminary comparison looks very close.
Well, if you design the hull correctly, that's half the battle, as you said. Now, what about the sails?
Let me show you some of the models and things that we've used in studies of sails.
Good. I can understand how sail works when you're going along with the wind, and the wind sort of pushes on the canvas and makes you go, but I wish you'd explain to us how it is that you can make a sailboat go into the wind or upwind or whatever you call it.
Well, part of the time when we sail, we go along with the wind directly behind us, or at a slight angle. And in that case, the wind operates on the sail just to push it along. But at other times, more normally, we sail at different angles to the wind. And in that case, the action of the wind on the sails is much like that on an airfoil or on a wing.
I mean, it really works like an airplane wing?
It really works like an airplane wing. And I think this little model is a good way to visualize that. The wing, when situated on an airplane, is subjected to flow that comes along in this fashion and over the top of the wing and also over the bottom, so that there's a difference in pressure on the top and the bottom surfaces, which results in a lift to support the airplane. Well, now we can take that same wing and rotate it in this fashion around to the attitude that it would have when on a sailing yacht. And let's represent this edge as the center line of the sailing yacht,
right,
and the wing, of course, is the sail. And the wind might come in at about this angle, so that there's flow around the leeward side of the sail and also the windward side. And that results, again, in a difference in pressure, so that because of the low pressure to leeward and the high pressure to windward, there is a force directed in about that way.
I see. That's sort of partly pointing forward and partly to the side.
That's right. And of course, it's the forward component of that total force that we really want to make large so that we can get high speed out of the boat.
So the boat is actually going in the direction the wind is coming from. That's the part that has always absolutely puzzled me.
The boat goes along that way. And of course, associated with that driving force, there is the component to the side, which, as we saw before, has to be resisted by the keel of the boat or by a centerboard.
So the boat doesn't just sort of drift sideways in the water.
That's
very
right.
interesting. It really works like a wing, then.
Well, besides our research on hulls here at MIT, we're doing some research on sails. And as a part of that work, we set up models, much of this form, but of larger models, at the Wright Brothers wind tunnel, and make tests to make determinations of the forces to be expected on sails of different forms. And in those tests, we set the model up in about this fashion and change the attitude, which would correspond to a change in the trim of the sail or a change in the heading of the boat. And we also run at different wind velocities.
Do you try different shapes and sizes and things?
Well,
yourself?
that's right. We vary a number of things. For one thing, we vary the amount of camber, that is the distance of offset of the sail here from a line through the leading edge and the trailing edge. And in addition to that, we can vary the position of the camber, whether it's up forward here near the mast or to the back.
Let's see. But a real wing isn't actually, a real sail isn't really shaped like a long thing like this. I think of it more as triangular, more like
well, that's
models.
right. And for that reason, we also test in the wind tunnel a more complete model, such as this one of a 12-meter boat. And this is a 1/15th scale model with the rigging exactly like a real 12-meter boat. But the sails in this case are solid rather than fabric.
Why is that?
Well, we found that, rather surprisingly, it's not possible to build a fabric model sail and have it conform to the proper shape in the wind tunnel that it would have out sailing. And so, to make tests at known sail shapes and chosen sail shapes, we construct these solid sails, and then we can get forces that correspond to whatever shapes we want. Now, in the wind tunnel, we tip the model at various heel angles, and also we have means to turn it through different angles of attack. I think it's sort of interesting, though, to point out that while here in the model tank, the tests are conducted with the model underway and the water fixed, in the wind tunnel, we move the air and keep the model in a fixed position.
That's right. But otherwise, they are rather similar.
But otherwise, the tests are equivalent.
And do you take the same sort of measurements and put them into a computer to see
That's
how
right.
real sails would work?
Very much equivalent to the hull work. We process the data, the measurements, and produce predictions of the full-size forces to be expected on different kinds of sails. Well, now, in addition to that, we've been doing another rather interesting type of test for sails, and we make use of another model, which I have here. It's right behind you if you pass it up.
This is a beauty. One of my kids would love to have this.
I'm sure they would. Well, this is a model much like the bigger one, but it was built for a set of tests that we did down at the smoke visualization tunnel at the Philadelphia Naval Shipyard. And those tests were strictly for the purpose of enabling us to visualize the flow around the sails. We put the model into a tunnel where the airflow comes in about this direction, and with the airflow are streams of smoke. And it's very interesting and very instructive to watch how the smoke streams are deflected around the leeward and windward sides of the sails. And I have a film which was taken during some of those tests which show the flow patterns in a way that we're really not able to see when we're out sailing a real boat.
All right, let's look at it.
The air, as shown by the streams of smoke, is coming from right to left, and we're viewing the boat from the leeward side. The boat is heel toward us and is progressing as though she were going to the right.
I see.
One of the very interesting things about these studies is the indication that the air is bent not just at the leading edge of the sail, but actually is bent quite a ways out forward of the sail.
It's interesting. The air is actually affected out in front of the boat itself.
That's right, and also quite a ways on each side of the sail, to windward and to leeward. And another interesting thing is that tip vortex that you see at the top of the sail, and that's a phenomenon common to every lifting surface, that because of the difference in pressure on the two sides, there is a rotary or vortex motion at the tip. Here the boat is positioned as though running before the wind or with the wind. And again, we're viewing from the bow, and the air, as shown by the smoke streams, is coming toward us. This is not exactly an ideal spinnaker. In fact, it's a transparent mylar sail that was shaped around my nephew's basketball. But at least it's a shape which indicates the flow that exists around the spinnaker. And it's been very useful to us to make these observations to show the form of the flow around the sails of an actual boat. We've looked at two types of research here, research on yacht hulls and also on the sails of the yachts. And now we have a means to combine the results of this research into a prediction of the actual performance of a boat. And for that purpose, we can use this time-sharing computer console. By calling the computer at the other side of the campus at the MIT Computation Center or by telephone, we can establish communication and use the typewriter to introduce problems and get back the solutions directly here.
I see. And there are other people at other locations who may also be working on problems at similar consoles.
That's right. We can all work at the same time, and the computer, as a matter of fact, sorts out whose problem it wants to do at each time, and it can do several problems at once. Well, the first step for us will be to tell the computer which one of our various programs we wish to use. And for that purpose, we'll type in Load Go SMGA. And that tells the computer to choose from its storage of programs one that's called SMG, standing for Speed Made Good to Windward. And in a moment, it'll give us an indication that it's picked out the right program, and then we can go ahead with our problem.
Right now, it's going and looking for your program that solves these problems.
That's right. And now it types execution, and then, as usual, the computer's very polite and it says, please type 0 to continue or 1 to stop. So we'll type 0 and let it continue. And that's an order to proceed to the next step in the program. And it now is typed, please type the hull test number. Well, it's asked us to give it the values which have been determined from test for any particular hull that we want to deal with. And I suggest we do a problem on the same hull that we looked at test results of earlier.
All right, this is that same one.
This is that same one. And if you tell me what the number of that test is, we'll communicate it to the computer.
This one here, 81.
81. Now the computer will search through its file of many test results, and it's already gathered all the information it needs about the hull. But it wants to know what are the sails that we're going to put on this boat.
Oh, surely.
Well, I can remember that for this particular boat, the sail area was 305 square feet. The next thing it wishes to know is the height of the center of effort of the sails, and in this case that was 16 feet.
Sort of the center of gravity, or where the wind
That's right.
might be acting if you concentrated it all in one point.
That's right. And then the third item that it needs to know is a value that indicates the righting moment of the hull, the tendency of the hull to right itself when heeled by the sail forces.
Oh, I see.
And that number in this case is 320. Now, to be sure that these values have been properly communicated to the computer, it will type back a systematic listing of these numbers. You see it says the sail area is 305, and the sail vertical moment arm is given here as 16, and the writing moment value is the same one that we introduced, 320. Now the computer console is typing a heading for the calculations that we want to make.
Let's see. Speed made good to windward. All right.
Speed made good to windward. Well, to visualize the problem, let's make use of this little model. And why don't we pretend that the wind is coming from a direction over there beyond the typewriter. And let's say that you're sailing the boat, and you want to arrange things to sail to windward as fast as possible.
I want to go that way
You want
into
to
the
go
wind?
that way.
Well, I don't think you can go right that way.
Well, first of all, I ought to ask you, what should the wind velocity be? Of course, actually, when you sail a boat, you don't usually have the chance to pick the wind velocity,
Right.
but we'll let you pick it.
Oh, I don't know. You pick a number.
Well, why don't we say 15 knots? And type that in. Now, the next thing that you've got to decide is how you're going to sail with reference to the wind. Are you going to sail at a wide angle or close to the wind?
I see what you mean. You go over that way and then come back. Well,
That's right.
all right, let's go in that direction.
All right, well, we'll start out sailing at about 60 degrees then.
All right.
We type in 60. And now the computer does a rather lengthy calculation. I say lengthy because it would take us several hours, but it can complete it almost immediately. And you'll see the result here is that the boat speed is 7.2 knots, but the component that is in the useful direction, the speed to windward, is only 1600ths of a knot.
I see I'm going off in a great rate off this direction, but I'm not making much progress in the way I want to go.
That's right.
Well, I'll head up into the wind. So.
Fine, we'll sail a little higher to the wind. Well then, let's say the wind velocity is the same as before, 15. And now we'll sail at, let's say, 30 degrees. The results are again being typed, and we'll see that as compared to last time, the boat speed is somewhat less, 6.09 knots compared to 7.2, but the useful part of it is now 4.12 knots.
All right, well, let's really point into the wind. I'll head up this way.
All right, well, let's say you're heading very high, about 10 degrees. And type that value in. And we'll see what the resulting sailing is. Oh, the computer has written us a note. It says, "Viewer and irons bear off." That's exactly the conclusion that you'd come to if you tried to sail a boat out on the water as close as 10 degrees to the wind. Well, now we could try many different choices of heading, and finally we'd arrive at one that was an optimum for the best speed made good to windward. And that would be the way you'd actually want to sail the boat, and we could make a similar calculation for other boats and determine what choices are best for good performance.
Well, thank you very much, Mr. Herreshoff. Today we visited the MIT ship model towing tank. Our guest has been Mr. Halsey Herreshoff. I'm John FItch, MIT science reporter.